Hello, everybody. Welcome back to RAT's Technical Sessions webinars. We have here a great presentation. I just want to mention a couple things. So apologize about not getting notice out for this one, but anyways, it happens. If you go to the website, you'll notice, I'm going to show you the website. We have a call for presentations at the top banner, and there's a pop-up there. So you can download this call for presentations. We're looking for presentations for the October 27th technical conference, which is going to be free to attend. Anyways, we're looking for some great presentations on rotating equipment, turbomachinery. And that is it. I'm going to keep it brief. I'm going to give it to Jared, and he can introduce Hydro.
Perfect. Thanks, Andrew. Yeah, so December 16th will actually be our last online webinar for the year. So look for that in the newsletter and on LinkedIn to get registered and share that around. And then as well, we are planning on January 20th next year to get back to Polos Lounge in person to do the live presentations and also implement a live webinar portion for the out-of-town viewers that we've been picking up as of lately, so that's always good. So for today's presentation, we got a really interesting topic that's been more in the limelight lately with all the reliability initiatives and efficiencies that people have been working on in Alberta and across Canada to get us more green and up to snuff there. So this presentation is going to focus on resonance, some of the methods that have been used in the field to mediate the issues, some of those experience that Hydro has had in doing that. And of course, we look forward to all the questions that you guys will be providing to us during the presentation so that Ralph and Glen can comment on that. So without further ado, I'll pass over to Ralph Fergusson, who is the account manager for Hydro Scotford Inc. And take it away, Ralph.
Perfect. Well, welcome everyone. Hydro Scotford is a 40,000 square foot facility located in Alberta's industrial heartland. Our motto is every repair is an opportunity for improvement. Every repair starts with a thorough inspection process, engineered review and support. Extensive process controls are at the heart of every piece of equipment repaired. The next slide there, Glen. Providing engineered solutions, working on all major pump manufacturers, focusing on operations needs, concerns, and problems. Hydro Scotford, it is an ISO 9001:2015 certified facility. ASME certified to repair, alter, or construct Section 8, Div 1, 31.1, and 31.3 category A, B, C, D, E, and H fittings. Canadian Welding Bureau to CSA standard W47.1, Division 2. We've internally developed and certified many weld procedures and are a member of the core partnering program certified through Alberta Construction Safety Association. Hydro Scotford is part of Hydro Inc. With approximately 20 worldwide service centers, being independent makes all the difference. Unbiased, solution-based rather than product-focused repairs, cost-effective solutions for technical problems, the Hydro advantage. Pump testing capability with their own in-house pump testing facility. Wire condition monitoring, Hydro's in-house Centaur wiring monitor system. Hydro Parts Solutions, quick turnaround of cast parts, including impellers, diffusers, pump casings, bowls, and bearing housings, allowing material and design improvements for hard to source or obsolete parts. Please contact me after the presentation if you'd like to discuss anything presented. And what brought you to today's presentation, Hydro Liabilities Service Group, expert troubleshooting and engineering for your rotating equipment. I'm pleased to introduce Glen Powell.
Hey guys, thanks for joining us today in the session. Just here's a quick introduction of myself. Hopefully you guys are all seeing the screen there. My name is Glen Powell. I'm a Category 3 vibration analyst, and I've been with Hydro for actually 9 years now. Worked at the service center at 40th Street near Chicago, and also at the test lab at 40th Street near Chicago. So you've got my contact information there. Look forward to the presentation today, and we'll go ahead and kick things off. One thing before we really get into it that I'd like to do is I'll pass it back to Andrew for a second so he can run a little bit of a poll just to give an idea, give us an idea of where people are at and what kind of level of experience and engagement you guys had with vibration. So I think that's up and running now. Is that right?
Yeah, I think it's should be showing there, hopefully. Collecting responses, it says, so hopefully people can see that.
Okay.
So
we'll give that a second to run.
5 choices. The first one's none, or I know that too high is bad and lower is better. Second one is only in theory, college, university, courses. I know enough to be dangerous, which is a pretty broad group of people. Gather, interpret, and or analyze data, like let's say a category 1 or 2, or detailed analysis, which I would consider a 3, 4, or beyond. So these are the categories that I created. Hopefully they make sense to you guys. Good amount of people have voted, so I'm going to shut it down, and we'll see. Let's share. Okay, so everybody has at least a little bit of theory, 14%. Like I said, half people know enough to be dangerous. And then there's the rest of everybody else, 36%, would consider themselves like a category 1 or 2 level to be able to analyze faults. But I think you're the only cat 3 on the call. So there you go.
Okay, well that's perfect. So I think that's really exactly where we want to be for this presentation. The idea here is to give people some perspective on vibration and how it relates to resonance. But we're not trying to make anybody a vibration expert in an hour-long presentation. We're trying to give you that kind of ideas and knowledge that you can take forward with you. So the goal of the presentation today is to talk about the sleeping giant, which in vibration problems is resonance. We see it all the time in field troubleshooting, bad actors that have very high amplitudes that nobody really has a reason for, nobody can really explain. And we want to give you some tools that you can take to those bad actor problems. So today we're going to primarily be discussing structural resonance. There's also a whole other category of resonance that we're not really going to get into, kind of rotor dynamics. But the ideas that we'll be tackling today, we're going to show you when to suspect resonance, how you can confirm it, what you do to confirm it. We'll talk a little bit about mode shapes, what they are, how they relate, and then ultimately, how you resolve it with an engineered solution. There's a lot of ways you can just get in there and start tinkering, but we'll show you some ways that you can actually get to a engineered solution. And hopefully, at the end of this, you'll have some perspective on how common resonance is and how you can deal with it. So we'll start out with some basics. I know everybody's got a little bit of familiarity, so we won't spend too much time. But the idea of vibration can be simplified mathematically to a very simple spring mass system. So you can imagine a mass concentrated at a point, and when you apply some displacement to it, when you lift it up, it's going to oscillate through that movement from up to down, the upper to the lower limit. And that kind of motion that's traced out is mathematically kind of the simplest basis for vibration. Now, the way we relate that kind of simple motion, that kind of simple harmonic motion to a rotating equipment, you can imagine instead of a point mass oscillating on a spring, you can imagine like a little heavy spot on a shaft as it's rotating around. As that spot rotates around, it also traces out a path that's very similar. So, in terms of the vertical movement of that spot, and that can be measured with a vibration transducer, any various number of vibration transducers. So, the basic terminology that you would kind of need to be familiar with to understand vibration would be a couple of things. The first thing would be the amplitude. So amplitude is just a measure of how severe vibrations are. So that can be measured from that first little red arrow there. That is just the height of the wave. Okay, we'll pause it there. So this amplitude could be measured from 0 to peak, could be measured from peak to peak. And you could also average that amount of energy in a particular wave, and that would be called the RMS, or root mean square. You also will have a period when the wave repeats. So from trough to trough or peak to peak, from 0 to 0, any of those would be the wavelength. And in terms of vibration, since we're talking in terms of time, we would call that the period, okay? So period is the cycle time. If we take the inverse of that, we would get the frequency. And the frequency is really the fundamental measure of vibration that is really important to us. Different frequencies are going to correspond to different faults and show up in different ways. The third characteristic of vibration that you need to know about is phase. And phase is sometimes the trickiest one to conceptualize, because any single point on a machine doesn't have phase. Phase is only in relation to different points on a machine. So from end to end of a bearing housing, from the motor to the pump, from different places. So this little example that I've got showing here is two fans that have got a little weight added to them. And you can see in the first instance where the weight is in the same spot, those two waves of vibration, they've got the same amplitude, they've got the same frequency, and they're in phase. If I were to put the weight on the opposite spot, now I have the same frequency and amplitude, but the characteristic is different. I've got a difference in phase. And this becomes really important, these kind of timing relationships between signals or vibrations, because if you want to know what's going on a whole machine, you need to know more than just what the amplitudes and the frequencies are. You need to kind of know how they relate to one another. And you'll see how this is important in resonance and natural frequencies when we get into that. So obviously, sinusoidal patterns are not really what you're going to see in terms of vibration. You're going to see much more complicated time waveforms if you're capturing that vibration in time. And the way that we analyze those is to break those complex time waveforms down using the fast Fourier transform method. And what that does is it takes this complex time waveform, splits it out into individual frequencies, which have their own amplitude and frequency. And once you have each of these split out individually, you recombine them in a different way to show a spectrum. So this is showing the frequency and amplitude instead of the time and amplitude, right? So we're going from the time domain, where we're just tracing out the motion, into the frequency domain, where we're understanding the different components of vibration that are present in that more complex signal. So we split it out into single frequencies, and then we recombine it into this form. Now, this vibration spectrum is really the key to doing all kinds of vibration analysis, and you'll see that in lots of different applications of vibration. But we'll take this one step further when we get into natural frequency and resonance. But this is kind of like the key to doing any kind of vibration analysis, is using the FFT to come up with a spectrum. Okay, so that's just all background basis. Hopefully a lot of those terms are familiar. I know it will be to most of you. So let's talk now a little bit about natural frequency. So if we want to understand resonance, we have to understand natural frequency. Structures, machines, everything around us has a certain frequency or frequencies that they want to vibrate at. And those frequencies are the natural frequencies. They're distinct from the frequencies that we see in operation of machines, in that these are kind of the undamped frequencies that they would vibrate at without any other input. So you can imagine a bell. If you ring the bell, the frequency that calls out from that bell is its natural frequency. And an even better example of this is a tuning fork. A tuning fork is designed to ring at a specific frequency, in order to produce a sound. So, those two kind of things are ringing at their natural frequencies because there's no forced vibration. It's a free vibration. Once it's excited, that's the vibration that it wants to experience. So machines, just like a bell or a tuning fork, have natural frequencies as well. They're just properties of the machine. They can be different on different parts of the machine. You could imagine the bearing housing on one end is going to be different than the other end. The casing of a pump is going to have different natural frequencies than the rotating element. But they all depend on the mass, and the stiffness in this little equation over here, this is just omega, this natural frequency depends on the square root of k over m, k being the stiffness and m being the mass. So if you remember back to the simple example of a spring in a mass system, the stiffness of that spring and the size of that mass are going to determine what the natural frequency of that system is. And when it's in that undamped condition, that natural frequency is what kind of drops out of the equation. So the thing you want to think about is that natural frequencies are a property of the system. It doesn't matter what job that machine is doing, it always has them. And the other thing to know is that you have different natural frequencies that are higher and higher and higher. I mean, theoretically, there's an infinite amount of natural frequencies for any structure. But the ones we're concerned about are the ones that could possibly be excited, the ones that are a little bit lower, frequency, natural frequencies. So, and again, when we talk about rotor dynamics, we talk about these in terms of critical speeds. That's not something we're really going to get into today, but that is a big component of understanding the operation of machines. I'm going to focus more in this presentation on structural resonance and how those can arise and what they look like. Okay, so that's the natural frequency side of it. In order to have a resonance, there also has to be a forcing frequency, okay? Forcing frequencies are the vibrations or frequencies that come up as a result of operating the machine, okay? So if you have a little bit of imbalance, that's going to show up as a particular frequency. If you have some misalignment, there's another frequency. Little vane pass in a pump, for example, you're going to have a frequency there. So those arise due to the way the machine is run. You're driving the machine, you're forcing the machine to do work for you, and the vibrations that result are the machine's forcing functions, forcing frequencies. So, you can imagine how you run the machine. You can change these. If you speed the machine up, if you slow it down, you can change those frequencies. Those are kind of in your control in some conditions. And this is different than the natural frequencies. The natural frequencies really just depend on how the machine is put together, the stiffness and the mass. But how you operate it doesn't really affect those natural frequencies. Okay, so the most common forcing frequency you're going to see, this is probably what everybody knows, is vibrations at the run speed of the machine, or 1 times. And that's very often going to be just due to imbalance or any kind of mechanical fault. Lots of different mechanical faults show up as 1 times vibrations. But there's lots of other peaks that can show up as well. You might have vane pass, you might have bearing frequencies, you might have some noise due to acoustical effects, flow noise. You might have line frequency, gear mesh frequencies, belt frequencies. So all these different peaks that show up in your spectra are going to be frequencies of interest when it comes to resonance. Okay, so that kind of brings us to resonance as a concept. And I'll give you, this is kind of the conceptual way that makes the most sense to me to understand resonance. If you imagine a kid swinging, swinging is kind of like a pendulum, right? A pendulum can be understood as a periodic motion or a vibration. And that swinging motion has a certain frequency. It depends on the mass and the length of the swing. So if you apply a forcing function, if you push, and you push with just the right timing, then you can affect an increase in the amplitude with very little force. If you push just at the apex, then you can get higher and higher amplitudes with very little input force. If you push too soon, in other words, too fast, or you push too late, too slow, then you're just going to take away from the momentum. You're going to steal from the momentum. But if you coincide your force with the natural frequency of the system, you can amplify the effect. So this is just a really simple conceptual idea of a resonant vibration. So if you time your pushes just right, you're going to get higher and higher amplitude. So, for us, where we're talking about machines, we don't want this situation. You are always going to want to avoid resonant excitation. And the reason for that is that your vibration amplitudes can be extremely high. you can get a 10 times, 50 times amplification of your amplitudes. Those elevated vibrations cause extremely high stresses. They can cause damage to the machine. They can cause failure over time, decrease reliability. So in our context of rotating equipment, you pretty much always want to avoid resonant excitation. So, a swing is one thing, but, for what we're dealing with, we always want to avoid the situation where our natural frequencies and our forcing functions are coinciding. And how we do that, or one of the things to keep in mind when we're doing that, is that, you need to have some sort of margin of separation between those two. So again, we're primarily discussing structural resonance. So in that context, the kind of common rule of thumb is that you'd like to have plus or minus 15% margin of separation between your natural frequency and your forcing function. So if we know both and we can set them where we want them, we would want to have at least 15% margin of separation. The reason for that is that you will be able to avoid that amplification if they're far enough away. The closer they are, the more amplification you're going to get. They don't need to be dead on, right? I don't need to have the natural frequency exactly on my forcing frequency in order to get an amplification. But to avoid it, think about plus or minus 15% is your rule of thumb. So, okay, again, that's all in the background. Let's talk a little bit about how, in practical terms, you would identify a resonance. I think this is kind of the meat and potatoes of why you would want to be here. So here's a couple of telltale signs. If you see a trend or a spectrum that has an unusually high amplitude, it's unusual, something doesn't seem right, it seems out of the ordinary, that's going to be your first cue. The second cue is high vibrations in one direction but not the other. So you can see here on this is a trend plot that's showing on the motor outboard the horizontal direction and the vertical direction of vibration. And there's a huge difference from horizontal to vertical. So that kind of highly directional vibration is oftentimes going to be present in a resonance situation. Okay. The next one that we'll talk about is bubbles of energy. So we'll kind of show you what that means, but sometimes the shape of the spectrum can give you an indication. And the last thing I'll show you is if you have changing speed and you have amplitude changes that result, you can have a kind of a tip-off that resonance could be involved. So again, this is a nice example of a highly directional vibration. Okay. And again, this is the same thing. You've got the red peak at the horizontal direction, and your blue peak at your vertical direction, and it's very small. So this big mismatch between horizontal and vertical, or horizontal and axial. If you have these big mismatch, it can be a big indicator. And again, this is just we haven't proved anything. We're just developing that suspicion. Again, this is another example of a highly directional vibration, horizontal to vertical. Here's an example of speed, and I wish I had speed plotted on this as well. It'd give you a little bit better idea. But what we're seeing here is this kind of the minimum speed for this machine, and this is over the course of running this machine up to full load and back down to the minimum load. You can see as we change the speed, the vertical direction spikes up in severity of vibration, then comes back down, and then the horizontal direction spikes up in severity, comes back down, and then when you get up to the maximum speed, you're kind of at this this low point compared to the others. If there was no resonant frequency that was being excited, you would expect the vibrations to just ramp up to the max at max speed and then ramp down to the minimum at the minimum speed. So when you see something like this, where you've got big changes with respect to speed, these speeds are going to be kind of a tip-off that, yeah, you may have a resonance problem at any of these speeds. So again, that's going to tip you off. We need to do some investigation into this. The last one that this is probably the one that I find the most useful is if you look at the spectrum and you see wide bubbles of energy right at the base of a peak. So here's a spectrum from a pump. Okay, so this has got a run speed here, that's this peak. I've got a little bit 2 times run speed peak here. It's not super high, but it's there. And then I've got this peak much higher than the others at vane pass. So this is a 5 vane impeller. It's just running at vane pass. So I think, what the heck is that doing there? Why is this so high? If I look down here, I see this bubble, okay? It's much easier to see this in logarithmic scale. This is linear scale right now. If I switch to logarithmic scale, you can see this kind of upside down V shape. This very wide base oftentimes indicates a natural frequency right there, right at the tip of this V is oftentimes going to be a natural frequency. And you can see that this vane pass peak, it's not dead on that V, it's just, it's interacting with it and you're getting some amplification. So those are some quick tips, quick tools you have. When you get vibration data, you may be able to build that suspicion. Of course, it's not sufficient to just have a suspicion that there's going to be a resonance problem. You have to do some confirmation of that. The way we would typically do that is through impact testing, sometimes called a impact natural frequency test or a bump test. This is something that you would do while the equipment is not running. You're going to impact the structure, typically with an instrumented hammer. So this is a force feedback hammer. I've got various tips. This is not a situation where you're going to use a claw hammer. You want to use something with a soft tip that's able to excite a broad range of frequencies. But this kind of calibrated hammer allows us to ring the structure the same way you would ring a bell, and then using instrumentation to listen back for the frequencies that come back. So you're literally just like a tuning fork or a bell, you're ringing it and allowing the natural frequencies to come back to you with your vibration instrumentation. For a different natural frequency, you might use a different hammer tip. If you want to excite lower frequencies, a softer tip. Higher frequencies, you'd use a firmer tip. But with a range of testing, you can kind of get a broad range of frequencies excited on a structure. And you can imagine if you have a very small light structure, you'd use a small modal hammer. Or you can, like Bob here, he's got the big modal hammer, and he's going to excite natural frequencies on this lake water pump. He's got a probably strike right here on the motor near the flange in order to excite that structure. So you might need more force for a bigger installation. For a smaller one, use a small hammer. Okay, so we have a method now. We know that natural frequencies can be identified with bump testing. Let's look at what that looks like. Okay, here's a KSB ring section pump that we had set up at the test lab in Chicago. If I look at the impact that I gave this, it looks like this. It's just a spike of energy, right, with a certain amount of force. Okay, so this is the force into the machine. And then the response on our instrumentation looks like this. It's responding to that impact and then kind of ringing down, right? This is an accelerometer that's attached to one of the bearing housings. It's responding and ringing down. And I can tell from this that we were impacting it in the vertical direction. Okay. What we get from that impact with the ring down, we pull a spectrum from that, okay, and we see kind of the response. So we impacted with the force in, we look at the response out, and we get a plot that looks like this. And what we're able to see from this is these different kind of upside down V shapes again, and these are going to be our resonant modes or our natural frequencies. So each one of these is a possibility for a natural frequency. And this is always extremely useful. If your machine is offline, you can do some quick bump testing, and you can find out, kind of where your problem areas are going to be. I can see right here at about 240 hertz, I'm going to be very likely to have a problem. And if I need to confirm it, I can use phase data. Okay, so phase data is used with something that's called a Bode plot. You plot the peak that you get along with the phase shift across that peak. And, in theory, mathematically, you should get a 180-degree phase shift across a peak, which is a natural frequency. So, if I have this data, I can look at a particular peak, look for the phase shift and confirm it where, this might be a natural frequency. This little hump right here, maybe it's just a little bit, I'd say like a sensitivity rather than a natural frequency, but you can confirm that with the phase data and a Bode plot. So again, this kind of frequency response idea, you're getting the output of the machine divided by the input. This picture, this is idealized. I mean, in reality, it's always going to be much messier than this, but I can show you kind of an example real quick of how that looks. This is a Bode plot from a natural frequency bump test on an actual machine, and you can see these 4 natural frequencies being identified, and the phase data down here, you see like across this 202 hertz peak, there's a nice phase shift. This little one, again, there's a phase shift, but these 2 peaks are kind of talking to each other mathematically, so it's not as clear. And the same thing here, I've got a phase shift across this peak, and then this larger peak, I've got a phase shift across it as well, but there's some kind of interaction between these 2 peaks, so you don't exactly get 180 degrees. I mean, in the real world, you don't need exactly 180 degrees to confirm that there's a peak there. What you want to see is a nice clean phase shift, as opposed to this kind of messy phases anywhere and everywhere type of data. So getting to this point where we have some idea of how we look at data and gain some suspicion, we do some bump testing, we're able to confirm those natural frequencies. Now we get into what those natural frequencies look like on the machine. And that is the concept of mode shapes. Okay, so mode shapes are the way that natural frequency is expressed in the machine physically. And those points have different nodes and antinodes. So that's going to be the next topic that we get into, but I know we're kind of close to the halfway point, so I thought I'd pause here, give everybody a chance to catch the breath and see if we have any questions on, I mean, what is honestly just kind of the theoretical background of what we're going into.
So we got a couple different ways to do that. There's a questions box, and then there's also the chat, so you can feel free to put that wherever. So Ralph Dickow has a question about, okay, I'm just going to read it word for word here. Some structures change stiffness with speed, i.e. the running, sorry, I can't remember what MNF means. Mean natural frequency, or anyways, could be different than static. What have you seen?
Yeah, so that's a really important one, especially with like rotor dynamics. You'll get different stiffness in the bearings or the components as you run up to speed. I would say, in my experience, typically like a structural natural frequency doesn't change much with speed. You're mostly going to be static with respect to speed. That's more something you have to worry about with rotor natural frequencies, critical speeds. But yeah, you know, it's something to be on the lookout for, but I'd say that's an uncommon situation for something to be changing stiffness with the speed of the machine. At least for, you know, typical industrial machines, pumps, turbines, compressors, motors, those are going to be pretty static structurally with respect to their speed, at least in my experience.
I guess we'll probably see some transient situations where, you know, temperature changes and, you know, differential expansions are happening.
Yeah, that's also really, I'm glad you brought that up. That's a really important point, is that with temperature change, yeah, you can get different natural frequencies because you're going to get different growth of the structure. And, you know, one thing that you will sometimes see is, you know, as something grows axially with thermal expansion, if it becomes bolt bound, then you can get some really different natural frequencies come up, because you're going to be in that, you know, where you're kind of twisting the case and having some effects there. So I would say kind of what I'm talking about is you've reached a steady state. If you haven't reached a steady state, I think it's very difficult to do this kind of analysis. You want to be in a steady state condition.
Yeah, I guess the caveat is that there are some machines that are set up for cold start, and there is no option.
Yeah. Well, one thing you can do is you can do a bump test at the cold condition, and also do a bump test. Well, if there's like a heat soak where they try to bring it up to the temperature. I know for some like boiler feed pumps, they'll do that type of thing. And you can do a bump test in both conditions, just like you do a cold alignment and a hot alignment. You can do a cold bump test and a hot bump test, and you may see some differences in the natural frequencies in that way.
Exactly. Yeah, it's just more of an investment in time and money, I guess, but could be useful information.
Yeah.
Okay. Well, I don't see any other questions at the moment. Did you want to continue, or when do we have that next poll?
We could kick the poll on right now. That would be let's do that.
Sure. We'll give everybody a chance to wake up a little bit. So, if you guys can see on your screen here, a dominant one-time peak in a spectrum is always due to imbalance. True or false? I'll give you guys a bit of a chance to put some answers in.
I'm hoping that's an easy one. That to me, come on, you guys have been around.
And it's not allowing the organizers or panelists to vote, so I can't vote.
Well, I'll just assume you're on top of that one.
Yeah. Okay, so it looks like people have woke up, started to vote. It's kind of stopped here. So I'm just gonna, for the sake of time, I'm gonna shut down the polling now. Okay, so looks like 33% say it's true, and the rest 2/3 of people say it's false.
Yeah, so this is a great question, because I think this is one of the major misconceptions on vibration analysis, is that your one times peak, a rotating equipment is always going to have some peak at round speed at one times. But one thing, if you can take one thing away from this, is that that one times peak is not always due to imbalance. Imbalance will give you a peak at one times, for sure. Anytime you have imbalance, it's going to contribute to that 1x peak. But if you have a perfectly balanced machine that's misaligned, you will get one times. If you have a perfectly balanced machine that has soft foot or looseness, you can get one times vibrations. So the place that you want to start is, okay, is the balance good? But usually that's a pretty easy one to rule out. If you have a machine that was recently repaired, you should get a balance report with it. You should be able to verify that. And if the balance is good, you have to start to look into these other causes: soft foot, misalignment, looseness, other things that are going on. So I keep that one in your heads. A dominant one times can be from a variety of different causes.
Okay, do you want to go into the next poll question, or did you have more slides to go?
I got a lot more slides, but we might as well do the other poll question now. Everybody's kind of awake at this point.
Yeah, okay, that sounds good. Okay, antinodes are the point of maximum displacement in a standing wave system. Again, true or false? I've got my answer. I don't know, I don't see any votes coming in. Oh, there we go. Maybe there's a bit of a delay in the system. Okay. The votes started to come in now. I think there's a delay in the system there. Okay, we're gonna shut it down right now. And I'll share that again. So 67% are saying true and 33% are saying false.
Yeah, so that's true. You've got, in a standing wave system, you've got nodes and antinodes, and one is representing the places where you have the maximum displacement, and then the other is representing the places where you have zero displacement. So that's actually a great cue kind of to get into the other part of the presentation here. So let me share the screen here. Hopefully we are back on my screen. Yep. Okay. So, in analyzing resonant frequencies, you'll find that natural frequencies not only have a particular frequency for the structure, but they have a particular mode shape. And so I've got a couple of different vertical pumps here, and you can see different mode shapes that arise. A first natural frequency might have this nice bending mode, and then you get into these higher frequency modes, and each one of them has a different amount of nodes and antinodes. So the thing that's interesting about this is that those modes depend, just like natural frequencies, on the stiffness, mass, and damping of the system, which also, of course, depends on how something is mounted. If I have a brace on my machine here, I'm going to have a different stiffness than if I have the brace down here. And you can imagine in these different situations, you would have different solutions to solve a natural frequency resonance problem. If I have this mode shape, it doesn't do me much good to brace it here where there's no motion. I need to brace it down here where the motion is at the maximum. So kind of right out of the gate gives you some idea of how mode shapes can be helpful. And mode shapes are used to characterize resonant vibrations. This is a discharge head, and you can see the different mode shapes that are, you can have this bending mode versus this rocking mode, for example. So again, you get this kind of idea of nodes and antinodes. And I kind of got ahead of myself on the slides here. Obviously, you would want to fix this in terms of bracing it where the maximum amplitude is. You wouldn't want to brace this down here where there's no displacement. You'd want to brace it up here where there's the maximum displacement. So how do we determine the mode shapes when we identify resonances, we identify natural frequencies in the system? The way that we go about creating this shape and understanding this shape is doing something called a modal analysis, okay? So now we're getting into how do we deal with resonance. So a modal analysis allows us to create those mode shapes, animate those mode shapes, understand them. And that starts with building a model of the system. So there's just a couple different systems here, a pump and motor with a little bit of the piping. I've got a discharge head and motor here. And, once you've built that modal system, you can get into doing the modal analysis. Some of you may have heard of a technique called operating deflection shape, or ODS. This is different than ODS. ODS is an online test where you measure the vibrations of a structure while it's running, but you don't really have an idea of what forces are exciting the structure. It's blind to those forces. A modal analysis is different. We're measuring the natural frequency of the structure, and it's a response to a known force, a controlled force. So we're inputting a controlled force and listening back and generating the motion or the mode of that structure as a result of that force. And the way we do that is the same way we do with impacting. We use impact with a calibrated modal hammer in order to give us that input to develop the mode shape. And so, kind of the key concept of modal analysis, it animates natural frequencies, identifies them. It allows us to troubleshoot those natural frequencies by showing us what the structure looks like. It assumes a rigid body, so you can't do a modal analysis of loosely bound components. They have to all be rigidly combined, which applies to most machines very well. And again, it's useful in how to deal with it. So if I set up a modal analysis, what I'm going to be doing is I'm going to be choosing a single point as a reference, and then using triaxial accelerometers all over the structure to take data on that structure, impacting in order to excite it, and then listening back all over the structure, okay? And since I have a single point of reference, I can map those responses simultaneously because I have a phase reference that goes back to one single point. So on a structure like this, you can kind of see the points that you might choose. So this is it's a crude but fairly accurate model of a real system. And what this ends up doing is it gives us these frequency response functions. And that's what you're seeing on the right. This is all the frequency response functions from all the accelerometers that I had on that discharge head and motor. And then when I stack them up, I can see the natural frequencies, okay? And then using modal analysis, I can zoom in on that particular frequency and animate what the structure looks like when it comes into resonance. So I can see on this discharge head, this particular natural frequency would be a rocking motion in the vertical direction, or in line with the discharge, in other words. If I go to this natural frequency at 13.3 hertz, so it's a little bit higher frequency, I can see that it's a horizontal rocking motion. Okay, so perpendicular to the discharge. And you can go to higher ones as well. This 23.9 hertz mode shape is very different. This is more of a torsional mode. This is a twisting motion. And you can see just from this right away, you would deal with these situations in very different ways. You know, if you want to stop the torsional motion, you're not necessarily gonna brace it in the same way as if you were stopping the horizontal rocking motion. And again, the same thing. If you get to higher frequencies, you can get to these higher mode shapes. Now you're getting into a bending shape that's a little bit more complex. And in general, as you go higher and higher in frequencies, you get more complex looking mode shapes. And to be honest, if you get high enough in frequencies, you start to lose confidence. You have to have a more and more accurate model with more and more points to accurately represent those mode shapes. So it gets kind of difficult. So, you know, for this particular problem where we were looking at, you know, this is just a kind of a summary table. What we would be looking to see is for the resonances that we identify, how do they compare to forcing functions that we see in the machine, okay? So we know from our previous testing, we have some bearing whirl vibration. We know we have vibrations at 1 times, and we can see which of these modes are going to be the worst for us. And we've identified in this particular case that this 13.3 hertz rocking mode is very likely to be excited by this bearing whirl forcing function. And you know, we had identified that bearing whirl function previously. So, you know, it just gives you some idea of, okay, this is a machine that has quite a few different issues with resonance, but in particular, this is the most likely one to be excited. Okay, so summary up to this point. We suspect we have a resonance. Maybe we saw highly directional, maybe we saw various things. We did some impact testing. We confirmed, yes, we have a natural frequency that's a problem. We did a modal analysis. We identified what that mode shape looks like. We identified that there's not enough margin of separation, and we saw the other modes. So we know if we make a shift, where those other modes are likely going to go. So now what do we do? In order to resolve a resonance problem, a structural resonance problem, you need to make a change to the stiffness, mass, or damping of the system in order to move that natural frequency or to suppress that natural frequency. And the thing to know about it is that the other modes are also going to move. So if I increase the stiffness to get that one mode to move, the other natural frequency rates are also going to move. And so if you want to be safe and you want to have an idea of what's going to happen as a result of a stiffness or a mass change, you know, it's very oftentimes going to be valuable to do some computational analysis. And we typically do that with FEA software. So I'm not going to go too deep dive into this, but you know, we've got a model of a BB5 barrel pump here, which had a resonance which was exciting this bearing housing. What we do by modeling it with the FEA software is it allows us to go through and test a lot of different methods for modifying the structure. So I can look at, let's say, putting a couple of ribs here. What's the effect going to be on the natural frequencies? Maybe I do a different pattern of ribs here. What's that effect going to be on the natural frequencies? And in fact, in this case, what we ended up doing was actually bracing on the other side of this, bracing that pump to the wall and adding stiffness that way. And that was ultimately the solution to that, was just adding bracing not to the base, but from the pump to the wall, which was a little bit of a out of the box solution for that one. But the nice thing about FEA is, again, if you wanted to try to tinker around and do these types of solutions in the workshop, you could be, you know, it's obviously not always going to be available. And, you know, the downtime of the machine to just try something is usually a bad idea. But in the FEA software, you can say, okay, what's going to be the effect of bracing it this way? What's going to be the effect of putting a kind of a double walled cam? What's going to be the effect of, you know, bracing all of the column pipes with ribs? And you can come up with not only the best solution for your installation to get rid of the natural frequency, but also, you know, what is going to be practical, what's going to be cost effective. This may be the best solution, but that's a lot of ribs to weld, you know, so you have to have those practical considerations as well. Okay, so real quick before we wrap, I have just a nice little case study that I think gives you some perspective on how this whole process goes. I know we kind of just went through the last part of it pretty quick, but let me show you this one. This is a a vertical pump at a coal-fired power plant. There's 3 units in this condensate system, the A, B, and C pumps. Only the C pump has been observed to have really high vibrations, and the customer's trying to figure out what's going on with it and why. We did some observations on this pump. We saw a highly directional vibration. Okay, so already it's very suspicious. Okay, most of that vibration energy is in the 1x. Okay, so we see a very high peak in the 1x. This is a recently repaired machine though, so this is not something that has a big imbalance, and I can go back and look at the history of that. I also see that this is very stable across the load rate of the plant. So it's a constant speed machine, but it varies in flow rate as the plant ramps up to maximum megawatts. And I see that really prominent 1x stays there regardless of the load rate. Okay, so we took it to the next step. We said, let's do a little bit of bump testing. We do some bump testing, and what do we see? This is 4 different directions, but I see this really strong peak right at 20 hertz. So this frequency response is bad news for us because our machine operates at 1180 RPM, which is right by 20 hertz. Okay, so we create our model. We decide we need to do some modal analysis, create our model. This is an ME scope. That's the software that we use for that. And then we take points all over the structure that looks like this. And then we're able to go in and animate the different modes and see what they look like. As it turns out, we've got this rocking mode right here at 19.1 hertz, and this is the offending mode. The structure wants to rock in this horizontal direction, perpendicular to the flow, and that's what's being excited when they run this pump. Okay, so then we develop an FEA model, a little bit more detailed. We can get into the can, the foundation, the base, and the beauty of this is we can take our data from the field, our modal data, and we can take our model in the computer, and we can make sure those 2 things are working together, that the experimental data and the computer model are predicting the same frequencies. And that's exactly what you see here. In the FEA model, I've got these first 2 modes. The first one is this vertical mode, where it's rocking in line with the discharge. That's at 16 hertz. And the horizontal mode, the one that's perpendicular to the discharge, that's at 19.1 hertz in our model. So it allows us to kind of validate that this computer solution is an accurate representation of reality. So what do we do in this situation? For this one, we looked at different ways to stiffen it, but in this case, stiffening it was a bit dicey, right? If we stiffen it, we're going to move the natural frequency up, but we risk moving this 16 hertz natural frequency up as well and bringing that one into excitation. So adding stiffness here, not the best solution. Instead, we added mass. So we literally went to the top of the motor, took this little cover off of here, which is about 110 pounds, and we added a mass on top of it of 2,300 pounds. So in the software, we're able to calculate for the customer, not just add some mass, but here's how much mass that you should add, and here's the effect that we think we're going to have. So again, with no weight installed, we've got this 19.1 hertz peak. And then with mass installed, we've shifted that peak down to 15.75 hertz. So that's the kind of effect that we're going for. And as a result of that, just by adding the mass, we end up dropping this peak at 1 times down by 66%. So this reduction in amplitude allowed this machine to be within the limits. And you can see this little bump down here. You can see the 1x is still right on 20. This little bump down here, that's our new resonant frequency right around 15.5 hertz. So I think that's just a nice little case study, shows you kind of how we go through the process, building up the suspicion, confirming it, doing the modal analysis to understand how it's moving, what other modes are around, and then that all informs the solution in the FEA. Do we want to stiffen? Do we want to add mass? How do we want to deal with it? So so that anyway, that's where we're at. I hopefully this kind of gives you some idea of where resonance come from, how you deal with it, how you can become aware of it. The thing I would caution you is that you ignore it at your peril. The vibrations that you can get due to resonance are extremely high. In that installation, the A and B pump were fine. The C pump was being excited. The suspicion is that there's been some structural degradation at that one. So it has lost some stiffness over time, and it's those natural frequencies have come into resonance. So, and if you want to have an engineered approach to the solution, that is something that you can do with this modal analysis, finite element analysis type of technique. That's it. This is kind of our little splash page. If there are projects and things that you guys have, bad actors or suspect resonance problems, and you want to talk to me, you've got my contact information in here, or Kyle, who couldn't be here for today's presentation. Yeah, that's what we do. We go into the field, we take troubleshooting data, come up with engineered solutions to try to get you out of bad situations. So hopefully there's a few minutes we can do for questions here at the end. Any questions as we kind of head toward the end of our presentation here?
Thanks, Glenn. And that was super informative. I really like the way you did that. And obviously, graphical and animations are critical for this kind of thing, to see how things work. Well, we don't have any questions right now, but I guess I had one, and this may not be your realm, but obviously we want to try and avoid these things at the beginning, right? Not put something out there into the field and then have issues. I mean, do you know of anything that's done, let's say at the design level, perhaps, to try and avoid these kinds of natural frequencies?
Yeah. Oftentimes, like new designs will go through this kind of study where they will predict the natural frequencies. But the difficulty that they have, or at least in my opinion, the difficulty that they have is that site conditions are not always going to be the same as test conditions. Like the bump testing we did at the test lab in the earlier example is a great example of this. That's a temporary setup, which has its own stiffness and mass to it. When I bolt that pump down in the field, I'm going to have different stiffness and mass. So, that test was done for the sake of the pump testing in the lab, to know that we weren't going to excite natural frequencies. You can give yourself some idea of what it's going to be in the field, but you're going to have different stiffness and mass in the field. So I think that's at the design level, they always try to avoid, bad critical speeds or bad natural frequencies. But sometimes when you get in the field, the reality is, you kind of have to update your model, so to speak.
Yeah, exactly. There's only so much you can do, and the base is different, the piping's different, the temperatures again, are different, and how you run it up and that sort of thing. So I guess yeah, the best you can do is just try to design it to avoid, and at least to understand what your natural frequencies are, and program
and
your.
also at the design level, you want to have that prediction, because if you go out in the field and you see a wildly different situation, that might be your first tip off that something's not right with your installation. Maybe you've got this massive pipe strain, you've got this twist and force in the case, and as a result of that, you're getting some natural frequencies that shouldn't be there. So I mean, having that kind of design level, at least reality check, is always going to be important.